Hi everyone, indeed it's a great pleasure to be back here in Cambridge after many years. So I was supervised by Mike Irwin and Richard McMahon, I guess last century. And I am now at the European Southern Observatory in Garching near Munich. And I'm an instrument scientist for a number of projects. So let me try and make this work for you, including the NIRPs, high-resolution spectrograph in the infrared that we put on the telescope in April last year. That's measuring radial velocity of exoplanets. And I'm a project scientist for Blue Muse, which is the blue version of a Muse integral field spectrograph on the VLT. And indeed, I'm working on UNDIS, which is the high-resolution spectrograph for the extremely large telescope, which we are currently building in Chile. I wanted just to show you some of the progress we are doing on site. This is from July last year, just to give you an idea of the size of the telescope that is being built currently. And we have more recently been able to rotate the dome structure on the ELT. So this is happening. We are building this giant telescope in Chile, and it's going to be equipped with a number of exciting instruments. If you're interested in any of these, please come and chat with me. So today I'd like to discuss a bit, the baryons in the universe. But before I do that, I'd like to start by convincing you again why baryons are important. And let me start by reviewing the component in the universe. Most of it, of course, is made of dark energy and dark matter. And I'm going to focus on the more normal matter by arguing that the light that is emitted by stars in galaxies only make 10% of the normal matter, right? So 90% of the baryons are in the form of gas, which is very difficult to study in emission. So this is one first point, but there is one more reason why baryons are important, and that's summarized in this plot, which is showing the dark matter power spectrum with baryon physics in the simulation implemented and with dark matter only, as a function of scale, where small scales are large K values. And what is showing as lines is the Millennium TNG simulation that has been recently outputted, and TNG 100 and TNG 300 expectation. So what we see is a deviation from a dark matter only simulation solely due to the baryonic physics in those small scales. And in particular, in the way we implement the active galactic nuclei feedback will affect the predictions we have on this dark matter power spectrum to a level that is greater than 10%, as shown here in the gray area. So it's very important for us to understand and implement in simulations this full physics of the baryons to be able to do this experiment of measuring the power spectrum. Now, what have we learned from simulations? This is an example of TNG 50 now, where we have gas that is coming from the cosmic web, being accreted onto galaxies through Lyman alpha radiation. So first, this gas is atomic, H1, and then becomes molecular, H2, which is the fuel for star formation. And then, supernovae and AGN will drive galactic winds that in turn will pollute the surrounding medium around galaxies in metal, energy, and mass. And this is now, in blue colors, a metallicity map of that same object. And these phenomena are happening around galaxy in what we call the Circum-Galactic Medium. The gas is moving with velocity typically of hundreds of kilometers per second in and out of galaxies. And this is what I would like to focus on. If you focus on H alpha only, one cannot capture these complex physical processes, right? So again, we need to learn from the gas itself rather than just from the starlight. This full cycle of material going onto galaxies and out of galaxies is what we refer to as the baryon cycle. So how can we probe that gas? One very powerful technique has been to use absorption line spectroscopy. So we're now using a bright background source, such as a quasar, or gamma ray burst, or fast radio bursts, to study the material along the line of sight to the observer. And this is done in absorption. I'm showing an example here of a very high signal-to-noise UV spectrum, where all the emission lines are intrinsic to the quasar, and the absorption lines are related to this gas along the line of sight, right? And so, of course, there's the Lyman alpha forest with many absorption lines, but also we have, information on the metals. So here I'm showing an example of silicon-4 and carbon-4. Now, this technique is very powerful for 3 reasons. First, we are directly counting the number of atoms, right? So we are measuring the number of atoms in H1, in H2, or in carbon, depending on the species we are looking at. Second, we are looking at low-density gas that would not emit much light. And thirdly, we use the same technique at any redshift, right? So the sensitivity of the technique depends on the brightness of the background source, and therefore if there is a bright enough high redshift quasar, then we are as sensitive as we are at low redshift. This is very powerful, of course. So let me ask a first question. How does the gas reservoir, which fuels the star formation, evolve with cosmic time? So we now know very well the building of a stellar mass over the universe and the star formation rate history shown here on the right. So this is, going from high redshift to low redshift. This is increasing. It goes at a peak value around redshift 1 to 2, and then it decreases again, which is not what we would naively expect from, star being formed as time goes on. So why is there this drop between redshift 2 and today? A large drop, right, of several orders of magnitudes. So let me go and reflect on the gas reservoir. So I'll start with the H1 atomic gas. This is a measurement of the observed mass density of atomic gas in the universe from redshift 0 to 5. This quantity, I'm going to show a number of plots of this quantity. So this is the mass density. On the right y-axis, you see it's expressed in units of solar masses per cubic megaparsec. And on the left, I've divided by rho crit at redshift 0, and it's now a unitless quantity. So we measure the amount of H1 gas from absorption systems at high redshift, at redshift 2 and above. And below that, we measure 21 centimeter at radio wavelength. So we have an accurate measurement of a global mass in atomic gas in the universe. And that quantity doesn't evolve very much with redshift. Now, if we look at the inset is showing the rate of change in mass from redshift 5. And again, the green is for atomic gas, but the pink is for stars. And what it shows is that redshift 2 or so, there is more mass in stars than there is in the H1 reservoir that was initiated to make those stars. So what's happening here? What's happening is probably we are not probing the full picture because we are missing the intermediate phase, which is made of molecular gas, H2. But recently, thanks to ALMA in particular, we've been able to use CO as a tracer of a molecular gas and make this similar plot of the mass density of molecular gas in the universe. So here the boxes are results from deep surveys, from Aspects and Colzi. I've shown you our own effort. So I'd like to introduce ALMA-Cal. This is a survey that is using the calibrators of ALMA. So every observation with ALMA has a phase and amplitude calibrator that are being observed. It's almost 20% of the total exposure time in ALMA. And I'm showing here in green the distribution of those sources on the sky. And we're using those cubes to look blindly for CO emitters, and that allows us to measure omega H2, which is shown here in red. And there's more work in progress with more recent data sets. So this works, I think, globally have still large error bars. We haven't, we're starting to measure these global quantities. And of course, it's very difficult to simulate this phase of a gas, right? The reason it's difficult is you need the cosmological, box size, but you need to also resolve very small scales, low density, 100 Kelvin gas. And there's a huge dynamical scale in between, which is very challenging. So I'd like to highlight some efforts that we are doing at MPN next door to include time-dependent non-equilibrium chemistry in a full cosmological box. And here I'm showing again the boxes are the observations, not that it's now going to redshift 2. And the lines are the predictions of our simulations. In black is the standard kind of evolution of making H2 molecular gas. and in red is the new simulation with this chemistry that increase the amount of H2 that we expect to have at low redshift and match better the observations. So I think this is some kind of work that needs to be happening in the coming years to be able to reproduce those observed quantity. Now, if I'm going to put everything together, here is again the mass density of baryons. So, and the blue at the top, I have plotted the total amount of baryons, which of course we know very well from, on one hand, anisotropy in the cosmic microwave background, from deuterium measurements and Big Bang nucleosynthesis, but also from measurement of dispersion measured in fast radio bursts. So this is a very well-known quantity. Most of the baryons are in the ionized phase, that is in the IGM, that I'm not plotting here, partly because it's very difficult to observe, but also because I'm concentrating on the phase of a gas, of a condensed matter that is making the stars. Again, in green, the neutral gas, in black, the molecular gas, and in pink, the stars. So 3 things to note here. First of all, the neutral gas in green, the H1, is always above the molecular gas at any redshift in the universe, right? So there is always more atomic gas than molecular gas. Now, we know how we derive this quantity. We've integrated the Coulomb density distribution, so that H1 gas is coming from massive quasar observer, 10 to the 23 and above. So this is related to galaxies. So if we want to study the gas in galaxies, even at high redshift, we have to care about the atomic gas. I think that's one important point. Another point is that the molecular gas, I think we have yet to be able to measure more accurately, but the current understanding is that the shape of a molecular gas is very much mirroring what we see from the star formation rate history, right? So it increases and then reach a plateau at redshift 2 to 1 and then decrease again. So let me concentrate on this a bit more and show you the depletion time. So I'm now looking at those quantities globally and looking at the amount of gas reservoir in different phases and the amount of star being formed. And so I'm not looking at the same objects, but I'm looking globally at those quantities, and I'm dividing one with the other because the depletion time, as shown here on the top right, is just the amount of gas divided by the rate at which this gas is converted into stars. If you concentrate on the gray area here, you see that the molecular depletion timescale is quite flat across a large redshift range, right? So what we're saying is there's something universal in the way we convert gas into stars. And the timescale is roughly 1 gigayear. In black here, I'm showing measurements in individual massive galaxies of stars formation and H2 gas, and they find similar results. This is work by Linda Tacconi and collaborators. And in blue here is the dynamical time. So at redshift less than 2, the dynamical time becomes larger than the depletion time, right? So this drop in the star formation rate history is likely driven by the lack of gas reservoir, right? So we are lacking gas, and therefore we are lacking the reservoir to make the stars. Now we went one step further and used those observables to infer the net accretion rate. So the question is, we know how much stars are being made, we know how much gas was there in the first place. How much more gas do I need to put into the system to explain all the stars that are formed, especially at low redshift? And this is now the purple line here, the bottom solid line. So this is really representing both the gas that is moving from the IGM into the ISM of galaxies. But it's also looking at the gas that is changing phase from ionized to neutral and atomic, right? So this is how much material is put into the galaxies to explain the star formation, right? And this is quite flat and then drops below redshift 1. So just for comparison, I'm shown here in black at the top, the accretion on dark halos. And I've scaled this to a 4% efficiency, and that's now the dotted line. So you see those two curves, the ones that we infer from observations and the one that is scaled down to a 4% efficiency, very much match each other. So this result, I think, is very much in line in what people refer to as a bath tube or regulator model, where galaxies have a steady state where, at early times, the gas is accumulating and then star formation is limited by this gas reservoir. And later on, then the galaxy reach a state where the star formation is regulated by the net accretion rate. So let me now focus on one subset of the baryons, the metals, the elements that are heavier than helium. And of course, a few years back, people here, Max and others, have looked at how much metal there is in the universe, comparing two observable. On one hand, the amount of stars that is being formed, modulo a yield of metal production to infer the total amount of expected metals. And on the other hand, the amount of metals that were observed in galaxies at high redshift. But before I go into this global quantity, let me just first look at how metals are distributed around galaxies. So I'm back on TNG 50 here. I picked a random halo. I've oriented it edge on. And on the left here is a metal map. So here in yellow is 0, so it's solar metallicity. -1 is a 10th solar, -2 is 100th solar. And what we see in this object is there are more metals along the minor axis of the galaxy, right? And on the right, I'm showing the gas radial velocity in the simulation, where green is gas moving onto the halo and the red is gas moving out. So we see a match, right? So the gas that is outflowing is more metal rich because the metal has been made in stars, in the ICM of galaxy. And although the accretion is isotropic, the accretion competes with the outflowing gas, and the path of least resistance along the minor axis is overtaking in the outflowing. So that's why the metals are along the minor axis. And here I'm defining this angle between the major axis and the minor axis as the azimuthal angle. This is now looking at hundreds of halos in TNG 50 with a cut in stellar mass and redshift, and it's showing the gas metallicity on the y-axis as a function of the radial velocity on the x-axis, where negative values is gas inflowing and positive values are gas outflowing. And this is color-coded with azimuthal angle. So what we see is that the gas that's falling onto halos statistically is less metal enriched, and it has a lower azimuthal angle, it's along the major axis. And gas that is outflowing of galaxies is metal enriched and it's along the minor axis. And now these are observables, right? Measuring the radial velocity of a gas is very challenging in observations, but measuring its metallicity and the azimuthal angle is possible. So these are predictions from both TNG 50 and Eagle, and I think it would be interesting to look at what observables can tell us on this very topic. Now that I've talked about metals around galaxy, let me move and talk about metals, across cosmic time. We can use those quasar absorber to very accurately measure the amount of metals in the neutral phase of a gas. This is shown here. The individual points are individual measurements. The black error bars are H1 weighted metallicity. And again, the solar metallicity is indicated as a horizontal line. And we see that there is an increase of metallicity over time. I think it's important to note that the scatter between individual points is much larger than the evolution overall. I'd like to stress that those measurements are corrected for dust depletion, so we use multi-element strategy to infer the true metallicity in that gas. And one last point is also indicated here, the current limits both at UV wavelength and optical wavelength. And we see that we don't detect low metallicity gas where we could from the current facilities. So this gas exists, but in a statistical sample like this one, it's very rare. So the pristine gas is very rare. Now we can use the same trick and measure the mass density of metals. So again, same color coding. In green here is for neutral gas. In purple is partially ionized gas. In blue is the ionized gas. We've concentrated here on very robust measurements, so there is some redshift gaps, but we can now compare this amount of metals with different phases. So the neutral phase dominates at our redshifts, and we can make a comparison with predictions from the essentially the expected amount of metals. So I'm showing here in blue what I call the expected amount of metals, which is essentially integrating the the mass buildup of stars modulo R factor, which is a return factor. right? And what we see is that at redshift 3 to 5, most of the expected metals are already in this neutral phase. Of course, at lower redshifts, there are other contributors to the metal budget. I'm showing here in pink the stellar metals, and in orange the hot gas metals that we find in intra-cluster medium and intra-group medium. So to put it together, I'm showing these pie diagrams in 4 different redshifts, where I'm dividing the amount of expected metals in the different phases of a gas we've been able to probe, or the different components. So if we go at high redshift, bottom right, most of the metals are found in the neutral gas. At redshift 3, bottom left, a large fraction is in the neutral phase of the gas, and some of the metals are found in more ionized phase. And then at redshift 0 or so, in the top left, actually most of the metal, half of the metals are in stars, of course, right? And the other contribution, the gas is contributing less to the metal budget. And the top right is showing redshift 1.5, where we have not yet measured some of these phases, some of the metals in these phases. So, the gray areas indicate what is currently unknown, but I think we are expecting that a lot of these metals are in the form of stars and hot metals that you will be able to survey with X-ray missions, such as, Crism and Athena. So overall, I think we have now been able to, allocate, recover all the expected metals at most redshifts in the universe. So I've talked about, some global quantities. I'd like to move now to, near to galaxy and talk about the galactic Baryon cycle, and in particular address the question of being able to probe the different gas flows in the Circum-Galactic Medium. The difficulty of this technique of quasar absorption is always to relate the gas we probe to galaxies, right? So here is a sketch of what we may expect. Some of the gas we probe may be related to the Circum-Galactic Medium of a halo. Maybe it's related to some satellite of that halo. Maybe it's a filament of accretion. Maybe it's another halo that just happened to be along the line of sight, but we haven't been able to quite decouple in velocity space. Thankfully, I think 3D spectroscopy has proven a true game changer to understand and relate the gas with galaxies. The idea is here, you take an image where every pixel is also a spectrum, so we have a full 3D information. One of example of 3D spectroscopy is MUSE on the VLTs, is KSAWI on Keck, of course. And we have a lot of information about the geometry setup between the galaxy and the gas in probing absorption. We have then information about the physical properties, including metallicity, but also gas kinematics. And there's been a number of efforts that I've listed here trying to associate the gas absorber with galaxies. Our efforts is rather unique by doing this at different wavelengths with the idea to be able to probe the multi-phase gas. Indeed, as mentioned multiple times, some of these gas, more external to galaxy may be ionized, but we believe the central ISM gas is likely to be more molecular. So the MUSE-ALMA halo survey is essentially selected on UV spectroscopy from HST to have non-H1 observer with a large column density of neutral gas that we then go and observe with MUSE to identify the galaxy in the field at the redshift of the observer. We do that also with ALMA to look at the molecular gas, and we've been recently allocated a large program to complete the sample. And then we had a medium proposal on HST to do multi-band broadband imaging to do a spectral energy distribution fitting and recover the stellar mass of each of these objects. So I've stressed that we know the H1 column density of those quasar absorbers. So here on the left, I'm showing the redshift distribution in green. And on the right, I'm showing the distribution of H1 column densities. So it's 10 to the 18 and above, very strong quasar observers. we've been looking at both the MUSE cubes and the HST imaging to recover above 3,000 sources, identify their redshift, measure their redshift, their star formation rates, their metallicity. And then we identified and matched the quasar observer with each of those galaxies. So one finding from these surveys that is also a finding of other surveys that are doing this kind of work is that more often than not, we find multiple galaxies associated with those quasar observers, right? So here I'm showing the number of observers that have a given number of galaxies associated with them on the x-axis, right? So some observer has none. We don't find a galaxy down to our detection limit associated with a quasar observer. And most have one, but some have 2, 3, 4, and more, right? And this is more than expected from a random distribution. So those strong H1 observer probe over densities of galaxies. So as I said, we've used this HST board imaging to do a SED fitting and measure the stellar mass of those objects. I'm showing here on the y-axis the H1 column density as a function of stellar mass on the x-axis. I think our detection limit means that we don't detect objects below 10 to the 8, and that's the cutoff here on the left. But you see a broad range of stellar mass in those objects, going from 10 to the 8 to 10 to the 12 even, right? So those H1 observers have all sorts of stellar masses. And there's a trend of decreasing H1 with higher stellar mass. Here is a plot that is a bit absorption-centric view. So we are now looking at how the atomic H1 gas is distributed around as a function of impact parameter, which is essentially the distance between the quasar sight line as you move away transversally. And I'm showing the results of MUSE ALMA halos in blue and other surveys at lower H1 column density, as well as 2 lines from Auriga and TNG50 again. So we see, as expected, that the H1 gas is quite extended away from galaxies, but the column density decreases with impact parameter, right? So we have a distribution that peaks in the middle and then fade away. Here is more galaxy-centric view. I'm showing the radius, the effective radius on the x-axis of galaxies as a function of this impact parameter on the y-axis. And now we are color-coding those points with H1 column density. And the red line is the virial radius of those galaxies. The blue line is RV over 2. You see that most observers lie below the blue line. So essentially, most of the gas-rich galaxies are located in region near the galactic centers of these galaxies. Here is a 2D plot of a gas around these galaxies. So I'm showing here the impact parameter on the x-axis and the velocity along the line of sight on the y-axis, color-coded with H1 column density. And again, you see that we can now move away from a folded plot to a map that shows that the H1 is peaking towards the center, near to the galaxy, and the column density are decreasing as we move away from galaxy, which is what we would expect from also simulations. So let me, just for fun, show you some of the data. Here is one field that has been observed with MUSE on the left and ALMA on the right. So we know the redshift of a quasar observer very well, so we can cut the cubes, like do fake narrow band, and look at where we expect on the left oxygen-free emission line that is going to trace the ionized gas, and on the right CO120, which is going to trace the molecular gas. And the other axis in the plane of the board is the wavelength or frequency, right? So I remove the quasar. This is the white square in the middle, in the plane of the sky. When you see a tube, this is a continuum detected galaxy. And when you see a blob, this is an emission, right? Oxygen-free or CO120. And yes, there is a match, right? So the objects that are detected in oxygen-free are also detected in CO. And now if you zoom in onto these objects, you see that the blobs are actually, have shapes that inform us on the kinematics of that gas in 2 different phases, right? So there's a lot of information in this 3D data, both in ALMA and in MUSE. So we've been able to reconstruct the kinematic of the gas We use an algorithm that is performing forward modeling, assuming 10 kinematic and spatial parameters to reconstruct the kinematics of that gas. On the right here, a result for one object in H alpha on the top and CO120 on the bottom. What we find is that both the molecular and ionized gas are aligned, but the molecular gas has velocities that are smaller than the ionized gas. You see here the color scale is different, and it's not as extended as the ionized gas, which is not necessarily what we see in our nearby galaxies. I'd like to highlight one example in particular where, again, we are showing here the velocity field of a galaxy, and the black point indicates the position of a background quasar. At the bottom, I'm showing the spectrum, the normalized spectrum of the background quasar, where the velocity of 0 is the systemic redshift of a galaxy. And what we find is one of the components, around 100 kilometers per second, is exactly matching expectation from the rotation of the disks that we can reconstruct from that velocity field. But the circled component in red here is both less metal rich, but also it has a higher, like 2 to 3 higher higher specific angular momentum, which means that it's a good candidate for gas accretion into this galaxy. So I think combining this emission and absorption allow us to probe those gas flow, both in accretion in outflowing. So the mental picture that we are building from this is very much like what we can see from this low redshift analog, right? So if you focus on the optical light, you have several objects, different galaxies, and then if you are able to observe at a radio wavelength, you see that there is some extended H1 gas in between those objects, low density, very difficult to detect in emission. And of course, if you focus on M82s, you have a school case example of galactic winds. So my point is, I think those strong quasar observers are a mixed bag of this phenomenon, and it's thanks to this multi-wavelength 3D information that we can combine together that we are able to disentangle what's making this gas-rich gas. Now, let me again ask the question starting from another angle, which is, what can we learn from cosmological simulation in terms of what is making that kind of gas? So we're back to TNG 50, and I'm showing here two different halos. On top, 10 to the 9, and at the bottom, 10 to the 11. The left column is color-coded in H1, atomic gas. So we're just projecting the halo, surface density of atomic gas. And on the right, we are labeling different particles according to whether they are associated to the central in blue, to a satellite in green, and then we define satellite as another halo which is within the virial radius of the central, or in yellow, other halos, something that is outside the virial radius but just happen to be along the line of sight. So I'd like to highlight this work is done by Simon Wang, who spent 2 years at ESO, but he's based in Sydney otherwise, and he's finishing now and very much looking for a job. So Simon's done this calculation, which is showing now the cumulative fraction of sightline as a function of a ratio between a satellite and a central. And there are 4 different colors for the for 4 different central stellar masses. The point to take away is, imagine you have a 10 to the 8 halo, right, which is below our detection limit in μs. If your central is 10 to the 11, then you are -3, or 10 to the 10, you are -2. Only 10% of the H1 gas is related to those satellites. But if your central is 10 to the 9, then you are -1. Up to 40% of the strong H1 observer that have been selected may be related to small satellites that are not detected, right? So this is a kind of new information, I think. Here's a plot I like very much, but let me walk you through this slowly. So this is now showing the fraction of sightline on the y-axis as a function of impact parameter. Again, using those labeling, right? So in blue is the central, in green are satellites, in yellow are other halos. Here I'm picking one panel where the central is at 10 to the 10, stellar mass 10 to the 10. And you see that as you're moving away from galaxies, your H1 is most likely to be related to the central. And then there's a contribution of some other halos, but also a contribution from satellites shown in green. And the symbols here are the result from Mu-Zalma halo. So we can compare these predictions from TNG50 with the observation. And you see it's broadly in agreement, right? So most of the small impact parameters are related to centrals, while we think that the higher impact parameter objects are related to the second halo term. Now, I'd like to spend a bit of time on the future, right? I've talked about some new results, but there's very many things to look forward to. And in particular, I would like to speak about how to progress this field by, I guess, going statistical. How can we, map the gas around galaxy in a statistical way, moving away from one by one object study? To this, I think the Foremost project is going to be key. So, like Foremost is a multi-object spectrograph that is going to go on a 4-meter telescope, the VISTA telescope in parallel. Foremost is a 3 square degrees field of view. It's composed of 2,500 fibers. It's a 5-year project that is going to start next year. And it's made of several different surveys, both consortium and community, that are combined together and share the focal plane, right? And like WIV, but unlike DESI, Foremost has 2 types of fibers with different spectral resolution. So obviously, most extragalactic surveys focus on using the low-resolution fibers, are of 6,000. And there are a number of surveys, including galaxy surveys with very high completeness that are evolving from gamma, the so-called waves surveys. There are studies of AGN, in particular following up E-Rosetta detections at optical wavelength, cluster groups, etc. And there's another set of high-resolution fibers. I'm showing a mock spectrum here. There are 3 spectrographs with huge gaps in between. I'd like to stress this. What we would like to do, what we will do, is record 1 million quasar spectra with the high-resolution fibers. I'm showing here a plot of number of quasar spectra as a function of spectral resolution for different ongoing and happening surveys. So in blue, we have ongoing surveys. Green are happening kind of surveys. So you see Sloan 4 on the top left, so 1 million quasars with a somewhat lower spectral resolution. DESI is shown here as well. Of course, WIV has 2 components, a low-resolution fiber surveys and a high-resolution fiber survey. At the bottom here, I've made an estimate of the number of quasar available in the ESO archive, both with X-Shooter, UVES, and in the future with UNDIS. And our effort is shown here in orange. So essentially, we're going to have spectra which are twice the X-Shooter spectral resolution, but we get 1,000 times more objects, or the latest Sloan release at 10 times the spectral resolution. So beside numbers, the idea of this so-called bicycle experiment is to use the low-resolution surveys that are studying the foreground object to match galaxies with magnesium-2 observers. So because we are sharing the focal plane, we'll be observing the same sky positions, and there will be spectra of AGN, clusters, galaxies, and we will look at the quasar behind those objects. So we are hoping to, so we've been allocated 2.8 million fiber hours. We are hoping to cross-match this 1 million quasar spectra with 1.5 million foreground objects. I'm showing here a foggy simulation of the experiment, and the bottom is a Foremost spectrum of magnesium-2 observer we are going to detect. The design is to look for quasar with redshift greater than 0.55 to have a magnesium-2 fall into the observed wavelength. We will look for Lyman limit systems, DLAs, and observer magnesium-2 and carbon-4. So there's a wide component that is going to survey the whole southern sky that is available from Foremost. And there's a deep component that is matching essentially the waves deep field with exposure time up to 50 hours. So we have been selecting those quasars from both Legacy Terran DR10 and Gaia DR3. So this is work done by Xing in Harvard. She has estimated, identified the sources as extra-galactic or stars for 2.8 billion objects, and then we've been able to measure photometric redshift for these objects. We have a very loose photometric redshift requirement. We just need them to be above 0.55, but the redshift of the object is not very important to this experiment. I'm showing here a plot just illustrating how well the photometric redshift match the spectroscopic redshift when there are none. And here, again, Simon's contributed to this work, is a distribution in terms of magnitude in blue and in terms of redshift in green. If you're interested, there will be, several thousands of very high redshift quasars, and they will be observed with a spectral resolution of 20,000. And those are fairly bright objects. So work has started already. We've used TNG50 to, doing some photoionization, post-processing, and ray tracing to make fake Formos spectra. So here is an orange, noisy Formos spectrum at high resolution that has TNG50 magnesium 2. I zoom in and show in green circles this doublet, magnesium 2 doublet. And what Roland has done is run a convolutional neural network to both identify spectra which have magnesium 2 and localize their position in wavelength. This is working very well. So I'm showing here a plot of a predicted position wavelength of a magnesium 2 observer as a function of true position. And you see that most of the objects recover very well with this CNN. So we have a 98% localization accuracy. Ultimately, what we want is to, map the gas around galaxies. I'm showing here recent result from data that is. So this is looking at many pairs of galaxies and quasar observers. On the left, this is a stack of the spectra, right? Median in red and mean in blue, and this is along the line of sight, of course. And on the right here is, again, the optical depth. So it's a measurement of the column density of a gas as a function of line of sight distance, or velocity on the right y-axis, and impact parameter, right? And so you see that there is, the optical depth decreases as you move away from galaxies in statistical sample. So those maps are very much smoothed, right? Because there is 100-ish pairs, galaxy quasar pairs, to make those maps. So what we will do with Bicycle is to increase by orders of magnitude the number of pairs to be able to really map the cold gas around galaxies. I'm showing this again from TNG50, looking at hundreds of 10 to the 10 halos, color-coded now in magnesium 2 column density. You see in red the little circle that indicates the current sensitivity in Sloan in terms of magnesium 2 column density. And in white here, contour, is what we will get with Bicycle, and the increased spectral resolution and increased number of quasar observer galaxy pairs. Right, so to wrap up, I'd like to summarize with some take-home messages. First, I think the star formation rate history drop at lower redshift is very much related to the gas reservoir that is being depleted, the H2 gas reservoir, and it's reflected in the decrease of a net accretion rate below redshift 2, which is related to the growth of the dark matter halo. I think a new multi-wavelength proof, the galactic Baryon cycle in individual objects is very powerful to find traces of accretion and galactic outflows. And of course, in the future, we very much look for this star Formos to be able to map the cold gas in the Circum-Galactic Medium. And with this, I'll thank you and be happy to take questions.